the hemoglobin level of the patient is below the lower limit of the reference range with respect to the age and then the gender of the individual. Because children, the reference range for children, HB, is actually different from the reference range for adults. And the reference range for females is actually different from the reference range for males. I did explain to you why males tend to have a higher HB or blood as compared to females. What makes male male is the presence of hormones, we call them androgens, particularly testosterone. Testosterone or the androgens actually contribute to the production of blood cells. And males technically have higher androgens level compared to their female counterparts. For this reason, males will have a higher amount of red blood cells and hence HB as compared to their female counterparts. Then again, in every month, females usually will undergo a period known as the menstruation. Males don't undergo menstruation, and when the female individual is menstruating, she is losing blood. And anytime you lose blood, you are losing iron. And once iron is being lost, you are on your journey to iron deficiency. And because iron is very important in the production of red blood cells, and for that matter, hemoglobin, once the iron level begins to decline, then that can result in anemia. Are we getting that? Okay, so we said that once you have been able to establish the anemia, and we can establish the anemia from the full blood count, the HB of the patient is low. Now the patient is anemic. So a low HB is equals to anemia. Now, this anemia is actually not a disease. Anemia is not a disease, but it is a condition. Anemia is an expression of a particular disease. One of the manifestations of somebody who has a chronic kidney failure is anemia, because the kidney actually contributes to the production of red blood cells. The kidney produces the hormone called erythropoietin. As the name implies, erythro is coming from erythrocytes. So erythropoietin is actually a hormone that is produced by the kidneys. And when it is being produced, as the name implies, this hormone travels to your bone marrow. So BM means bone marrow, and stimulates your bone marrow to produce RBCs, red blood cells. This implies that when the kidney fails, that is, there is a kidney failure. Kidney failure means that the kidney has failed in every aspect of its function. And if one of the functions of the kidney is to produce erythropoietin, and we are saying that this is a kidney failure, then it will equally fail in producing the erythropoietin. And once we know that this is the hormone that is supposed to stimulate your bone marrow to produce RBCs, this means that kidney failure will result in a decreased erythropoietin level and hence a decreased stimulation of the bone marrow, and that results in the release of lesser or decreased amount of RBCs. And the decreased amounts of RBC is called anemia. So when the RBC count is low, that is anemia. So in this particular context, the anemia is not the disease, but it is the kidney failure that is the disease. And the expression of the failure is the anemia. Therefore, anemia is a condition, but it is not a disease. It is an expression of a particular disease. If you get malaria, malaria is the disease. One of the expression or the symptom of malaria is anemia. So it is the malaria that is the disease and not the anemia. Anemia is just one of the manifestations of anemia, of the disease. If somebody has a sickle cell disease and the red blood cells are rapidly being broken down, and it results in anemia. The disease is not the anemia, but the disease actually is the sickle cell. And one of the manifestations of the sickle cell is the anemia. I hope we are together. Okay. So, we said that once you have established the anemia, we want to know what is actually responsible for what? The anemia. You know, we just said that the anemia is not the disease. So we want to know what is causing what? The anemia. And that will bring us to the classification of what? The anemia. So what we have to do now is to classify the anemia. So classification of anemia. Classification of anemia. Basically, there are two major classifications of anemia. And these two major classifications of anemia are etiological classification. Then the second one is the morphological classification of the anemia. Morphological classification. The word etiology means cause. What etiology is the study of what? The causes of what? Disease. Etiology is the scientific word for cause, or medicine word for cause. Cause is just an English word. When we translate cause to medicine language, it is called what? Etiology. So we have classification of anemia. We can classify the anemia based on what is causing the anemia. Then we can also classify the anemia based on what? The morphology. That is, we want to look at the red blood cells, the shape, the size, the color, and that will fall under morphology. Morphology is the study of what? Form. And if you are studying the form of something, you will study the shape of that thing, you study the size of that particular object, then you study the color of that particular object. So morphological classification will basically be looking at the size of your red blood cells, the color of your red blood cells, the shape of your red blood cells. So then when we looked at the etiological classification, that is point number 1. We looked at the etiological classification. So under the etiological classification, these are the possible classifications. And we said blood loss. Blood loss. So loss of blood, whether you were involved in an accident, being it a car accident, motor accident, or you have been stabbed in the course of what? A fight, it can result in blood loss. Or the blood loss, maybe you were menstruating, and after the normal period that we are expecting that the menses is supposed to cease, you are still losing blood, but this time it is in drops, smaller volumes, and that means that you are losing the blood. That is called the chronic blood loss. So we have blood loss. Then the next one, that is B, we have inadequate production. So you have anemia, and the doctor wants to find out what is causing the anemia. The doctor will be asking the patient to find out whether if there is any history of blood loss. If it's a female subject, the doctor will want to find out when she menstruated and whether the menstruation has stopped or it is still ongoing. Then the doctor will be able to establish. The doctor will also ask, when you go to the washroom, do you pass out blood in your stool, to know whether you are bleeding through your GIT. So under the blood loss, we can have acute blood loss, and then we have what? Chronic blood loss. The acute blood loss is losing large volumes of blood within a short period of time. whilst the chronic blood loss is losing smaller volumes of blood for a longer period of time. Somebody can still be menstruating. The menstrual flow will be coming up to 6 months, 7 months, even up to a year. That is chronic blood loss. If somebody is involved in a motor accident now and they rush the person to the hospital and they stop their blood from flowing, then that is an acute blood loss. You are losing large volumes of blood within a short period of time. And the inadequate production, we know that blood cells are actually produced from the bone marrow. And so, is it the case that your bone marrow is having a problem? Because the production center of the red blood cells is the bone marrow. And so we can query the bone marrow if there is a bone marrow disorder. So inadequate production can occur as a result of a bone marrow failure. So when there is a bone marrow failure, there can be a decreased production of the RBCs. That's number one. To produce the red blood cells, we need ingredients. And the ingredients to produce the red blood cells include iron, vitamin B12, folic acid, certain proteins. And so all those ingredients must be available in order for us to produce the blood cells. And so inadequate production can be an issue with the bone marrow or the resources needed for the production of the red blood cells. Then the next one is destruction. So destruction of the blood cells. The red blood cells have been produced all right in their adequate numbers. For some reason, you were bitten by an infected female Anopheles mosquito and you had malaria. The bone marrow has produced adequate numbers of red blood cells in circulation. The malaria parasite enters into your red blood cells and begins to break down the red blood cell. And that is not a problem with the bone marrow, but there is something external causing destruction to the red blood cell. And so destruction is also called hemolysis. Hemolysis. So that is hemolysis or hemolytic anemia. So destruction can be as a result of an infectious agent, such in the case of malaria parasite destroying your red blood cells. And as many red blood cells are being destroyed, it is expected that the machinery for the production of red blood cells needs to be activated to produce those red blood cells that have been destroyed by the malaria parasites, as an illustration. If the bone marrow is trying to compensate, assuming that thousands RBCs have been destroyed by the malaria parasites, in order for anemia not to occur, the bone marrow must produce an equivalent number of thousands to balance the destroyed one. If the bone marrow fails to produce an equivalent number of RBCs up to the 1,000, then there is an imbalance. Say, for instance, thousands RBCs are being destroyed. The bone marrow produces, let's say, 800 RBCs. The remaining 200 creates a gap, or there's a deficit. This means that the bone marrow is unable to compensate for the destroyed RBCs. And when production is lower than that which has been destroyed, then anemia occurs. So anemia occurs when destruction or the hemolysis of the RBCs exceeds the production of the RBCs. So once production is lower than what has been destroyed, then anemia occurs. Anemia will not occur if the bone marrow is able to produce to compensate that which has been been destroyed. A patient is having sickle cell disease, either SS or SC. Once you are having a sickle cell disease, the general rule is that when the patient is exposed, the system is exposed to an environment where there is low oxygen, then it will trigger the crisis. Patient is not drinking adequate fluids or water. It can create an increased viscosity, and that can trigger the crisis. And when the crisis happens, the RBCs are going to be destroyed. as many RBCs are being destroyed, it is expected that the production center must compensate the destroyed RBCs. And the production center is the bone marrow. The bone marrow will not be able to compensate for that destruction because the destruction will be so much that it will not be able to compensate. And if it is not able to compensate for the destroyed RBCs, then anemia what occurs. So sickle cell, malaria, G6PD deficiency. G6PD is an enzyme that is found in the membrane of the red blood cells. And we all know that this enzyme actually protects your red blood cells from becoming damaged by certain drugs. We call them oxidants. And we describe oxidants as reactive oxygen species or destructive oxygen species that actually damages our cells through the membrane. So once you are G6PD deficient, you are deficient of the G6PD enzyme, deficient of the G6PD enzyme, and you take in a drug that we call it oxidant drug, then your red blood cells begins to break down. And once the red blood cells are being broken down, that is what hemolytic anemia. So hemolytic anemia, or the destruction of the blood cells, is one of the causes of anemia. So G6PD is the commonest. Sickle cell, malaria, all these ones are common causes of this, pregnant women, because G6PD can cause a destruction. G6PD deficiency can result in the destruction of the red blood cells. Before a pregnant woman can be placed on the SP drug, the sulfadoxine pyrimethamine drug, we need to do the G6PD test, because it's the G6PD enzyme that will protect your red blood cell from becoming damaged by oxidants. The drug that is given to the pregnant woman is an oxidant, and because it is an oxidant, it can trigger the hemolysis or the breakdown of the red blood cells if the G6PD enzyme is absent. So we test the pregnant woman to see whether the G6PD enzyme is present or not in order to prevent the hemolysis when the drug is being given to the woman. So basically, under the etiological classification of anemia can be classified in terms of blood loss, and the blood loss can be acute, that is losing large volumes of blood within a short period of time, or it can be chronic. You don't lose large volume, but you lose it in smaller volumes for an extended period of time, usually in months. Acute blood loss usually lasts in hours up to days, whilst chronic blood loss lasts up to months. Then we also mention inadequate production, which means that when the bone marrow is failing, it will not be able to produce adequate amount of red blood cells, or the resources, the ingredients required for the production of red blood cells. If the ingredients are not available, then there is going to be a decrease in the production of red blood cells, and that results in anemia. Or the bone marrow has produced enough red blood cells in circulation, but something else is busy destroying them in circulation. And that is what we call destruction or hemolysis. And we gave illustration of such: sickle cell disease, G6PD deficiency, malaria. They can all cause the destruction of the red blood cells. And when the destruction exceeds what the bone marrow can produce, then that results in deficit, and the deficit is what we call anemia. Then we want to look at the morphological classification of anemia. Morphological classification of anemia. But before that,
concerning the inadequate production of blood cells, I'm contemplating on considering the quantity of erythropoietin produced as to the one which stimulates its number of RBCs which we produce. The more the erythropoietin, the more blood cells we produce. The smaller you have the folic acid, the B12, and also you have the iron. Though they are conditioned, they affect the morphology and also with the breakdown or the differentiation of the cells. So in this situation, linking them around as the erythropoietin connects
erythropoietin, kidney failure also is part of inadequate production of red blood cells. When the kidney fails, there is going to be a failure, because I just linked it up. Once there is a kidney failure, there is going to be a decrease in the production of erythropoietin. And once the erythropoietin production decreases, then we know this is the one going to stimulate your bone marrow to produce what? The red blood cells. And the kidneys have failed. Failure of the kidney means it has failed in all the functions. Just name it. All the functions of the kidneys, you know. Once we say kidney failure, it has failed in all those functions. All those functions are not carried out properly. Are you talking about the removal of what? Waste substances from the blood? It has failed. It means that the waste will be accumulating in the blood. Are you talking about the regulation of electrolyte? It has failed. All the regulation will not take place. Are you talking about the production of erythropoietin? It will no longer produce it. Or even to produce it inadequate. And if it is inadequate, since this is the stimulatory factor for RBC production, then less erythropoietin production will mean that a decreased stimulation of the bone marrow. And hence, once the bone marrow has been stimulated in a lower level, then that means that RBC production is also going to be what? Reduced. And a reduction in the RBC is what we call anemia. So, kidney failure, anemia due to kidney disease, is as a result of inadequate production. You can have your iron, you can have your folic acid, you can have your B12, let them all be available. But if the erythropoietin is like a catalyst. It isn't that when an enzyme is absent in a chemical reaction, the reaction cannot occur. What do we define an enzyme to be? We say an enzyme is a biological catalyst that speeds up the rate of a chemical reaction. It means that when the enzyme is absent, it will go on, but it will not, the speed will not be there. So erythropoietin is only a stimulator. If the stimulator is not there, the bone marrow will produce the red blood cell, all right, but not in adequate what? Amount. Are you getting that? So kidney failure will fall under the inadequate what? Production. Patients who are even on chemotherapy, chemo patient, cancer patient, they give them drugs. And the drugs, the side effect of some of those drugs is the suppression of your bone marrow. Your bone marrow, which is supposed to produce RBCs, the side effects of the drug is that it will affect the bone marrow. Not because it will suppress the bone marrow, they will not treat the cancer. So they will give you the drug to treat the cancer whilst they are monitoring the bone marrow. And they monitor the bone marrow by checking, doing the FVC. Full blood count can be used to monitor the bone marrow. So the full blood count is used to monitor the bone marrow function. So patients who are on chemotherapy, it will also result in inadequate production. Are we together? Okay. So we want to look at the morphological classification of the anemia. In the morphological classification of anemia, anemia can be classified using the red cell indices. So we classify the anemia. So classification is done using the red cell indices. Red cell indices. And these red cell indices are part of the complete or the full blood count. And these are the red cell indices. We have the MCV, which is reported in femtoliters. We have the MCH, which is reported in picograms. We have the MCHC, which is reported in gram per deciliter. So when you want to classify the anemia morphologically, we use the red cell indices. The M here, they all denote what? Mean or average. So this is mean cell volume. All this is talking about only red blood cells. So when we say mean cell volume, we are talking about the volume. Mean means average. So the average volume of the red blood cell is known as the mean cell volume. And volume, in this particular context, volume actually of the red blood cell is synonymous to the size. So the mean cell volume is actually referring to the size of the red blood cell. So is the average volume or the size of what? The red blood cell. So that is an inference we can draw from the MCV. So the MCV is actually an average volume of the volume or the size of the red blood cells. And once we are talking about the size or the volume of the red blood cells, you know, the volume can either be lower, it can be what? Normal, or it can be what? Higher. So the size of an object can either be small. So the size of the RBCs can be small. Anything that is small is called micro. But this object that is small is a cell, and a cell is a site. So that becomes microcytic. The size of the RBC can assume a normal shape, so normal cell size, and anything normal is called normal. And because it's a cell, it becomes normocytic. The size of the RBC can be larger, and anything large is macro, either large or big, macrocytic. So based on the morphological classification of what? The anemia, using the red cell index MCV, mean cell volume, which is a measure of the average, that is for the mean, the average size or volume of the red cells. The volume or the size of the red blood cell can be small. In that case, we say we are dealing with microcytic what? Red cells. Or we can have normal RBC sizes, and that is called normocytic RBCs. Or the cell sizes are larger than normal, and that is what? Macrocytic. When you know these classification, each of these classification actually points to a particular cause. There is something that is making the red blood cell size becoming smaller. There is something that is making the red blood cell size becoming normal even when there is anemia. There is something that is accounting for the red blood cell sizes becoming larger in the presence of what? Anemia. This, when the size, if the HB of the patient is what? Low, and the red blood cell sizes, MCV is, let's say, the MCV is what? Low. A low MCV means that the cells are what? Smaller. If the MCV is normal, it means the cells are having normal size. If the MCV is high, from the full blood count report, it means that the cell sizes are what? Larger, and that is what? Macrocytic. Once the HB of the patient is low, and you find out that the MCV of the patient is what? Low. In other words, the cell sizes are smaller. It means you are dealing with microcytic anemia, because the HB is low, so that becomes a microcytic anemia. If the MCV is rather normal and the HB is low, that becomes normocytic anemia. If the MCV is high and the patient is having anemia, then that becomes macrocytic anemia. Are we together? Good. So now, if you want to look at the causes of microcytic anemia, we want to find out what is causing microcytic what? Anemia. Why is the red blood cell sizes becoming smaller in the face of what? This kind of what? Anemia. So if you want to look at the causes of a low MCV or causes of microcytic anemia. So causes of microcytic anemia. One of the commonest causes of microcytic anemia, or what makes red blood cell sizes to become smaller than normal, is the ingredient we call iron. So iron deficiency is a common cause of microcytic anemia. Not all anemia is as a result of what? Iron what? Deficiency. Yes, sometimes you hear on radio, a person is sitting on TV and say that once the HB is low, then you are having iron deficiency. HB, a low anemia is when you don't have enough iron. That is not the case, because we have so many causes of what? Anemia. So the causes of microcytic anemia is iron deficiency what? Anemia. Are we together? Now, iron deficiency is the commonest what? Cause. Once we know that iron deficiency is the commonest cause, if it is not enough for you to say that, oh, when I checked, the patient MCV was what? Low, the HB was low, so microcytic anemia. So I think that is iron deficiency. Patient can start taking what? Iron supplement. You might be wrong. You have to now find out the iron deficiency you are talking about, which is the cause of microcytic anemia. Even that iron deficiency also have cause. So what are the possible causes of what? Iron deficiency what? Anemia. Could it be that the patient is having a hookworm or parasitic infection? How do you know whether the patient is having a parasitic what? Infection? That will mean that you have to do a follow-up laboratory test. So knowing that a patient MCV is low, microcytic anemia, one of the follow-up tests is that patients should go and do stool RE, stool routine examination. So that when the lab man examines the stool, the lab man will be looking for parasites in what? The stool. Once we find out that there is an egg or an ova of a parasite in the stool, then we know that is the parasite that is causing the iron deficiency. Therefore, to effectively treat this patient, you must target the parasite by giving those drugs that can kill the parasite. Once you eliminate the parasite, the iron will be meaningful. When you give the iron to the patient, it will be of use. Otherwise, if you do not strike the root cause by doing further investigation, take for instance, if it is hookworm infection that is causing the iron deficiency, and you are only giving the patient iron supplement, you know what? You are not nourishing the patient, but you are nourishing the hookworm. So it is the hookworm rather you are feeding, because anytime the patient takes in the iron, the hookworm will feed on it. The hookworm will feed on it. So the patient can only respond to the anemia, and the anemia can be corrected only by identifying the cause, and that is the etiological. So iron deficiency in itself has causes. So you do stool RE. You check, you can, based on history, you can find out from the patient why the patient is urinating blood in the urine. There is no organ in the human body that excretes iron. But anytime you lose a single red blood cell, you have lost an iron, because iron is found in the hemoglobin, and hemoglobin is found in the red blood cell. So if you lost a red blood cell, you have lost iron. And so if the patient is urinating blood or urinating, the urine color is red, it suggests that red blood cells are coming into what? The urine. And once red blood cells are going into the urine, then it explains why there is possible iron deficiency and hence microcytic what? Anemia. In that case, we need to find out whether there is a parasite behind the patient urinating the blood, such in the case of the parasite called schistosoma. So we have the schistosoma hematobium. Schistosoma hematobium. This is a parasite that attacks your bladder and then causes the RBC to leak into it, so it can possibly result in what? Anemia. So you do urine RE. So urinary will solve the problem. If the urinary reveals that there are a lot of over of schistosoma hematobium, you give the drug, and the drug for the schistosoma hematobium, you destroy it, then you can now give iron supplement, and that will be of use. Maybe the patient is bleeding through the GIT, gastrointestinal bleeding. Not all patients that are bleeding through the GIT that you see blood in the stool. Some of them are bleeding, but when they bleed, the blood gets digested in as part of the stool. So the stool will come out clean. There is nothing like blood stain in there. There is only one test that you can perform to determine whether the patient is bleeding through the GIT, even though you have not visibly seen the blood. And that test is called the stool occult blood test. Occult blood test. The word occult means something hidden. Occultism, people who practice occultism are people who hide somewhere. They don't want people to see them. So once we use the word occult, we mean hidden blood. And something that is hidden, you cannot see it with your naked eye. So we do a stool occult blood test. We use some tablets, we call them the Guaic tablets. Then you mix that one with the stool. If it comes out that it is positive, it means that the patient is bleeding through the GIT. And possibly it will be the reason for the iron deficiency. And once you establish that occult blood test is positive, it can be that there is a tumor in the GIT. You have to do further tests, ultrasonography. For example, they can do colonoscopy, ultrasound scan. They do colonoscopy to find out whether if there is a growth that is there and that is causing, the patient to bleed and causing the blood in the stool. So stool occult blood test. So we do not just say that microcytic anemia is just prescribed. It is only in situations where you cannot do further laboratory investigations. Then you go ahead and suggest iron supplement or diet that is rich in iron for the patient. And if it gets corrected, then that is lucky enough for the patient. Otherwise, when the patient is not responding, it will demand for further laboratory investigation. So iron deficiency, the most common cause of microcytic anemia. The next one is lead poisoning. Lead poisoning. Lead poisoning can cause a picture of iron deficiency. This one, you can get this information by asking the patient the occupation. So the patient, what work do you do? You go to the magazine, the fitter where they are working, they will suck all the petrol, all the metals are in their mouth. They cannot say that, or they are not guaranteed 100% that all those metals that come in contact with their mouth, they never take part of the lead into their system. So as the lead metal is accumulating in their system, it can result in iron deficiency. It actually interferes with the metabolism of iron, and that results in iron deficiency. It will result in, it creates a picture of iron deficiency, but it is not iron deficiency. So at the end of the day, it interferes with the effective utilization of the iron, and that will result in microcytic anemia. So lead poisoning can result. Once we ask the patient the work he does and ask whether the patient has been putting those lead metals or something into their mouth, then it can be a cause of lead poisoning. That microcytic anemia you are getting is lead poisoning. Then there's another one, the third one, we have another cause of iron deficiency. Another cause of microcytic anemia. Number 3 is sideroblastic anemia. In sideroblastic anemia, the iron is there, the iron is available, but they are stored in the organelles, the mitochondria of the cell. It is not made available to the bone marrow. So iron is actually available, but they are stored in cells, we call them siderocytes. And those cells actually don't release the iron, siderocytes. Iron is not actually released. And so it is not made available to the bone marrow for the bone marrow to actually use the iron for RBC production. So this is the common one. Then another one, 4 of 1, thalassemia. Thalassemia. So thalassemia is actually a hemoglobinopathy. Thalassemia is a type of hemoglobinopathy. Hemoglobinopathy. Pathy means disease. What is now left here is hemoglobin. Hemoglobinopathy, therefore, is a disease of hemoglobin. Disease means disorder. So hemoglobinopathy will mean disorders of hemoglobins. So disorders of hemoglobins is called hemoglobinopathy. And one of the hemoglobinopathies is thalassemia. In thalassemia, what happens is that the hemoglobin molecules has changed. Every hemoglobin, listen to the name, hemoglobin. Hemoglobin. This means that hemoglobin has heme and globin. The globin is made up of chains. We have, when we take hemoglobin A, the normal adult hemoglobin, we have alpha chains and we have beta chains. There are actually two alpha chains, 2 beta chains. When you take the fetal hemoglobin, it has 2 alpha chains, 2 gamma chains. When you take hemoglobin A2, which is part of the adult hemoglobin, it's made up of 2 alpha chains, 2 delta chains. Now, these are globin chains. So the globin chains can exist in terms of alpha chains, beta chains. In thalassemia, what happens is that one of these globin chains, there is a reduction in the production of the globin chains. So if, let's say that there is a reduction in the alpha globin chains, then that is called alpha thalassemia. Is the reduction affecting the beta globin chain, then that is called beta thalassemia. Are we together? So thalassemia is actually a genetic disorder where there is a reduction in the production of the globin chains. And one common thalassemia, there are various types of thalassemia. We have thalassemia minor and thalassemia major. The thalassemia minor is the one that portrays the features or that display the features of microcytic anemia morphologically. So now, we have been able to establish that the red cell indices that we can use to classify or describe the morphology of the red blood cells, they include the MCV, which is the mean cell volume, and that will give us a picture of averagely the sizes of the red blood cells. And we said that when the size of the red blood cells are smaller, in the full blood count reports, what will make us to know that your red blood cell sizes actually are smaller is the MCV value. If the MCV value, the machine flags that it is low, it means that averagely the cells are smaller. I mean your red blood cells. And that is microcytic anemia. We want to find out what could possibly cause the red blood cell sizes to become smaller. And we said that a common cause of microcytic anemia is iron deficiency. And we said, do not just go straight ahead as a clinician to just giving iron supplement to the patient. The iron, which is the common cause of microcytic anemia, also has causes. So we look at the causes of iron deficiency, and we said that find out whether if the patient is bleeding through the GIT. A stool occult blood test will find out whether there is bleeding through the GIT. And if it is positive, you can do colonoscopy to check whether there is a tumor. We can also do stool RE, stool routine examination, to check whether if there are parasites. When you see the egg or ova of a parasite, it means the patient has a parasitic infection. And the parasite is actually feeding on the iron of the patient. So once you give those drugs that will usually kill the worms, and you succeed in destroying the worm, then the iron you are prescribing to the patient will be now of what value. Then we also look at the urinary. The patient might be losing RBCs through the urine, and once you are losing RBCs, you are losing iron, and iron is an important component when it comes to the synthesis of what? Red blood cells, and for that matter, hemoglobin. So we do urinary to check whether there is a parasite in what? The urine of what? The patient. Then we said that apart from the iron deficiency being the common cause of microcytic anemia, we could have lead poisoning, and the occupation of the patient will help us to know whether it is a case of what? Lead poisoning. Lead test is not common in our district facilities, so you cannot easily perform lead poisoning. So clinicians usually ask of the occupation to know whether it is an issue or the disorder or the abnormality is as a result of what? Lead poisoning. Then we look at sideroblastic anemia, where there is iron available, but the iron are not being utilized, and they are captured in cells. We call them siderocytes, and that is the sideroblastic anemia. It will make the cell size become smaller, because if we are not making use of the iron, then the iron, what are we using it for? It means that we cannot use the iron to synthesize the RBC, so the RBC sizes become what? Smaller than normal. Once iron is deficient, we know we use iron to synthesize hemoglobin, and hemoglobin is found inside the red blood cells. The lower the amount of iron, the lesser the amount of hemoglobin inside the red blood cells. And the lesser the hemoglobin, the smaller the size of what? The red blood cells. Then we also spoke about thalassemia. And we said thalassemia actually is a genetic disorder that actually refers to a reduction in the synthesis of what? The globin chain. And if the globin chain that the synthesis is being reduced is the alpha, that becomes alpha thalassemia. If it is the beta chain that the synthesis is being reduced, that becomes beta thalassemia. And so the thalassemia also occur in types, apart from defining it in terms of what? Alpha and beta thalassemia, gamma thalassemia, or delta thalassemia. We have thalassemia minor, we have thalassemia major. Typically, the thalassemia called thalassemia minor is the one that will make the red blood cell sizes to become smaller than normal. That is microcytic what? Red cells. So that is just for an MCV being low. We want to look at an MCV being high, a higher MCV. When the MCV is high, according to the full blood count report, it means the cells are macrocytic. Macrocytic. Is the HB of the patient low? Yes. If the HB of the patient is low, then that becomes macrocytic anemia. Are we together? So the anemia only comes in when you know that the HB of the patient is what? Low. But if only the MCV is the one that you cannot add anemia to it. So macrocytic what? Anemia. Once there is macrocytic anemia, we also want to find out the possible causes of what? Macrocytic anemia. Typically what it means is that your cells, the red blood cell sizes are bigger or larger than normal. So we want to establish what are the possible causes of what? Larger than normal RBCs. So macrocytic anemia. So basically there are two types of macrocytic anemia. We have megaloblastic anemia, and non-megaloblastic anemia. Non-megaloblastic. So these are the two major causes of what? Macrocytic what? Anemia. Or sorry, the two main types of macrocytic anemia. So we have the megaloblastic anemia and the non-megaloblastic what? Anemia. So the megaloblastic anemia is actually due to, so the causes of megaloblastic anemia include folic acid deficiency, folic acid or folate deficiency. Then we have the vitamin B12 deficiency. So megaloblastic what? Anemia. So we are saying that once the MCV of the patient in the full blood count is high, then it means that the cells of the patient are larger than normal. Larger than normal RBCs are called macrocytic, and if there is an anemia, I mean the HB is low, then that becomes microcytic anemia. There are two types of macrocytic anemia, namely megaloblastic anemia. Mega means bigger, so that the cell sizes are bigger than normal, and we also have non-megaloblastic anemia. And the common causes of megaloblastic anemia is folic and vitamin B12. So we want to establish the reason why folic acid or folate or vitamin B12 deficiency can make the red blood cell sizes become larger than normal. These nutrients are actually essential ingredients in the synthesis of DNA. These are essential ingredients in the synthesis of DNA for every cell to undergo cell division. What controls cell division? DNA controls cell division. DNA controls what? Controls cell division. Cell division. Any cell without a DNA can never divide. And the DNA, we can trace it. If I have a cell, the central part of the cell is the nucleus. The nucleus is made up of nucleic acids. And the nucleic acid is either DNA and RNA. So the DNA is found in the nucleus in a broader picture. So any cell without nucleus cannot undergo cell division because the DNA is found in the nucleus. So this folic acid or folate or vitamin B12, they are the ingredients or the raw materials that are used to synthesize what? The DNA. And so if these are the ingredients to synthesize the DNA, and this DNA, its function is that for any cell to undergo division, it is the DNA that controls what? The cell division. What this implies is that when vitamin B12 and folic acid are deficient, then the synthesis of DNA is going to be impaired. So there's going to be an impaired or decrease, an impaired synthesis of DNA in the face of folic acid or folate deficiency and vitamin B12 deficiency. And once the DNA synthesis is being impaired, it can no longer control the cell from dividing. The end result is that the cell keeps on growing larger than normal and can never divide to give rise to other cells. You know, mitosis is supposed to occur as the cells are being produced. And because the DNA synthesis is being impaired, there is going to be a failure of mitosis. So a single red blood cell, instead of dividing to give rise to multiple RBCs, that single red blood cell will continue to stay single and grow larger than normal. So once it happens this way, then we say the cell is bigger than normal, and that is what we call megaloblastic anemia. So folic acid, vitamin B12 are the common causes of megaloblastic anemia. The whole issue is that we don't have them to synthesize DNA, and once DNA synthesis is impaired, there is going to be a loss in the division. And when the cells fails to divide, then it implies that the cell will rather grow larger than normal. And a larger than normal red blood cell is called megaloblastic anemia. The non-megaloblastic anemia mostly is as a result of chronic diseases. Alcohol abuse can result in non-megaloblastic anemia. So in that case, the MCV is also still high, but it is not as a result of folic acid or vitamin B12 deficiency. Liver disease, alcohol abuse, and some form of thyroid disorders, they can cause non-megaloblastic anemia. So that is it for the MCV being high. So but the common one is the vitamin B12 and folic acid deficiency. The MCV of the patient could be normal, and if it is normal, then that is what? Normocytic. And that becomes what? If the HB is low, then that becomes normocytic what? Anemia. So we want to establish the causes of normocytic what?
With the megaloblastic anemia, we know that the first identified was inside the peripheral smear, or it's going to still move to the retic or reticulocyte stage.
None of those are seen in the peripheral blood smear. It's not normoblast, it's not erythro, none of those stages. What we are talking about, the word blast, as used here, it appears to give you like a picture as if there is blast in there. But it is, blasts generally are cells that are bigger. Are you getting it? So blast cells are generally bigger than the matured ones. So megaloblastic actually refers to those red blood cells in circulation, in peripheral, that are actually bigger. We are just likening the blast to what is found in the bone marrow. Not that in megaloblastic anemia we are seeing blasts. Are you getting the picture? So those blasts are not found in the peripheral blood smear. They are inside the bone marrow. And when you collect blood from the patient vein, you don't enter into the bone. So those blasts are inside. Actually, we are not seeing blasts in the peripheral blood smear, or we are not seeing the blasts in the thing from the slide when you are observing under the microscope. We are not seeing the blasts, but we see larger RBCs. And when you do a thin film, that reminds me, when you do a thin blood film, once, I told you that full blood count and peripheral film comment, they go hand in hand. The two are actually inseparable. You can't separate them. So once, whether it is microcytic anemia, normocytic anemia, any form, you have to do a thin blood film. In the case of megaloblastic anemia, if you actually want to know whether it's a megaloblastic anemia, peripheral film comment can actually suggest that, or can give us about 90% conclusion that this is megaloblastic. Of a patient who is having megaloblastic anemia, peripheral blood smear, we'll be looking for neutrophils. And when you see the neutrophils in the smear, neutrophils generally have 2 to 5 lobes. They have 2 to 5 lobes or 2 to 5 segmentations. Neutrophil, they have about 2 to 5 lobes. And what happens is that in megaloblastic anemia, 2 to 5 lobes means that if you see this one, for instance, this is a neutrophil. How many lobes is it having? 1, 2, 3. 3 lobes. So, if I have a cell this way, how many lobes is this particular neutrophil having? 1, 2, 3, 4, 5, 6. Normal neutrophil has 2 to 5 lobes. When the number of lobes that a neutrophil is having is above 5, then we call that one hypersegmentation. All these ones are segmentations. Hypersegmented neutrophils. So hypersegmentation. So once you see a hypersegmented neutrophil in your peripheral blood smear, it points out to megaloblastic anemia. So in megaloblastic anemia, the neutrophils are hypersegmented. There is hypersegmentation of the neutrophil. So once the clinician or the physician or the nurse, they see that there is hypersegmentation, then they will know that this is a typical case of what? Megaloblastic anemia. And that will be what can be used to differentiate between megaloblastic anemia from non-megaloblastic anemia. In megaloblastic anemia, there is hypersegmentation of the neutrophils, whilst in non-megaloblastic anemia, there is no hypersegmentation. Are we together? Good. Then the MCV, we say that is normal, then it means you are dealing with what? Nomocytic what? Anemia. And once we say that the anemia, you have anemia, that is what? Nomocytic anemia. The question now is, if there is anemia, why is it that the red cells are normal in size? Why is the red blood cells normal in size? You see, anemia has nothing to do with the size of the red blood cell. Anemia means the number of the red blood cells have reduced. It is not about the size of the red blood cell. So the size of the red blood cell can be normal. Size is not number. We are talking about how many red blood cells are available in the patient's system. Are they enough? Yes. Then you are normal. Are they enough? No, they are low. Then that is anemia. So nomocytic anemia, when there is anemia attached to nomocytic, it means that in terms of numbers, your red blood cell count is low, or the HB value of the patient is what? Low. But in terms of size, your red blood, even though you have anemia, but the sizes of the red blood cells are normal. A clear illustration of nomocytic anemia is kidney disease. Kidney failure. In kidney failure, the kidney has failed to produce what? Erythropoietin. And because there is a decreased production, so kidney failure results in a decreased production of erythropoietin. And that will also mean that there is going to be a decreased stimulation of what? The bone marrow. And a decreased stimulation of the bone marrow means that there is going to be a decreased production of what? RBCs. And that will be equals to what? Anemia. So it is that this anemia is all about this erythropoietin level being low. It is not that the anemia is as a result of erythropoietin is not iron. It is not folic acid. It is not vitamin B12. So there is no way. You are only going to stimulate the bone marrow. So of what effect do you have on the size of the red blood cell? You do not have any effect. You are only coming to trigger me to produce more. But if your level is low, you do not affect in any way my size. So in kidney failure, where there is a decrease in the production of erythropoietin, and for that matter, a decrease in the production of the RBCs, it is just that the RBCs are not enough. And because it is not enough, that is why we say there is anemia. And the RBCs that are available, since erythropoietin is not a nutrient, it cannot in any way affect the size of the RBCs. And so that is why we say that even though the RBCs are not enough, we call it anemia, but the sizes are normal. So that is nomocytic anemia. Are we okay with that? So nomocytic what? Anemia. That is under the condition that before the patient had the kidney failure, there is no underlying nutritional deficiency. But before you had your kidney failure, you were already deficient of iron, you're already deficient of vitamin B12. It means that we will not get that picture as what is expected of the type of anemia in the case of what? A kidney or renal what? Failure. Are we there? Good. So, bone marrow kidney failure will result in what? Nomocytic anemia. Are we okay with that? Then again, bone marrow. This one. There's nothing, your kidneys are okay. But even your bone marrow itself is failing. Bone marrow failure. Are you having a bone marrow? There can be a disease of your bone. So bone marrow failure, a disease of the bone marrow, can also result in a decreased production of what? The RBCs. So bone marrow disease or bone marrow failure can also result in nomocytic what? Anemia. Patients who are on chemotherapy, chemo, you receive some drugs and the drugs went and suppressed the bone marrow. It has just suppressed the bone marrow. It isn't that the bone marrow cannot produce red blood cell at all. It isn't that the bone marrow has been shut down completely. The bone marrow is actually working, but the drugs have actually suppressed it from performing its full responsibility by producing adequate number of RBCs. And because the RBCs are inadequate, that is equals to anemia. But the inadequate, the available RBCs that we say they are inadequate, their sizes are actually normal. Under the condition that there was no nutritional or prior nutritional deficiency before the patient was put on the chemo. So, patient who is having G6P deficiency, you are deficient of the G6PD enzyme, and you didn't know, and you had malaria, or you didn't know, and then you went and took a drug that has what? That has sulfur inside it. That drug will trigger, oxidative stress, and that results in the breakdown of the RBCs. So red blood cells have been broken down. What the full blood count, the result the full blood count brought out and said the RBC count is low. It didn't count those one that has been destroyed. It only counted after the destruction. What is left is what it has counted. And it says that the RBCs left are actually low, and that is called anemia. But the available RBCs are actually normal in size, so that is what? Nomocytic. So in general, hemolytic anemia mostly will fall under nomocytic what? Anemia. Are we here? Good. And if you want to do, if it is hemolytic anemia, all the case, all the time, if you do a peripheral blood film comment, you will see a lot of polychromatic cells, because once the bone marrow is actually working and responding to the anemia, you see polychromatic cells. And polychromatic cells are reticulocytes. But peripheral blood smear, we don't call them reticulocytes. We call them polychromatic what? Cells. So that is it for nomocytic what? Anemia. And then some form of viral infection. There's a virus we call the B19 virus. B19. This virus can shut your bone marrow for even up to 1 to 2 weeks. Once the B19, it attacks your RBC precursors, the ones that are inside your bone marrow, and shut your bone marrow for up to 2 weeks or 3 weeks. This explains why sickle cell people, their RBC lifespan is averagely 21 days. So when they get an infection of the B19 is going to stop your bone marrow it's going to shut your bone marrow for 2 weeks. It is going to shut your bone marrow for 2 weeks. A sickle cell patient is most likely to die. B19. The B19 virus. I think it's a parvovirus. The B19 virus. So this B19 can shut down the bone marrow for 2 weeks. If somebody who is not having sickle cell, that is the AA person, gets the B19 infection, that person will survive, because your red blood cell, so we are looking at SS versus AA. The SS, their lifespan, RBC is 21 days. AA is 120. When I shut the SS bone marrow for 2 weeks, maybe even the RBC will get finished, because 21 days, some have already spent their lifespan, so some they will be dying. But when I shut the bone marrow of an AA person just for 2 weeks, the lifespan, the available red blood cells in circulation are going to live up to 120 days. So if you can shut it even for 1 month, the person will be okay. You can even shut it for 2 months, the person will still be okay. But you are shutting the bone marrow of an SS person for 2 weeks, 3 weeks, and the lifespan is around 21 days, the person will die. Are you getting it? So a B19 viral infection, shutting the bone marrow, the available is usually, even though it has shut it down, some few RBCs will come out in the circulation, But when the anemia occurs, the anemia typically does not affect the size of the red blood cells. And typically that will also be a hemocytic anemia. So that is it for the MCV being normal. Do you have a question? Now I want us to do some, the full black, I want us to look at some calculations, the formulas involved in it before I look at the case study. So we know the MCV. The MCV, which is reported in what? Femtoliters. What do we need in order to calculate the red cell indices? We need the HB of the patient. Is that not it? We need the hematocrit. What is the other name for hematocrit? Packed cell what? Volume. Or hematocrit. Then we also need what? The RBC. So hemoglobin, PCV, or hematocrit. Then we need RBCs. So let me number them. 1, 2, 3. So the HB, PCV, or HCT, RBC. These are the parameters we use in calculating the red cell indices. Okay. So now the MCV, which is mean cell volume. Which is what? Mean cell volume. We know PCV. Mean cell volume is the answer for the average size of a single red blood cell, not all the red blood cells. If I sum up all of you here, your ages, and they say your mean age here is 17, that 17 represents a single person's age. That is averagely a single person age is around 17. Are you getting that? So we want to find the mean cell volume. I want to deduce the formula. The formula, I don't want to write it. But for all the many RBCs, you have millions of RBCs. And these millions of RBCs is giving you a volume. And this volume, we call it what? The PCV. Then what will be the volume of a single red blood cell? That means, if this number of red blood cells will give us a volume we call the PCV, then to get the volume of a single red blood cell, then divide the total volume by the total number of RBCs, then you get the volume for what? A single RBC. And that is what we call the mean cell what? Volume. Which is the same thing as what? Hematocrit. So MCV is equals what? Hematocrit over RBC. We want to change this formula. I want to do some calculations, and the formula will change a bit. So there is actually a factor here that will be times 10. And that will be the formula for this 10 is a conversion factor. If you want the shortcut, it's hematocrit over RBC times 10. And that will send you to the unit to what? Femtoliters. And that will send the unit to what? To femtoliters. So now, let's see how we will prove. So let's look at how we prove this formula. So MCV so let me put it this way. MCV is equal to hematocrit over what? RBC. But we know hematocrit is usually in what? Percentage. RBC is usually times 10 to the power 6 per liter. You know that. That's the unit. I'm introducing the unit. So this means that this is the same thing as hematocrit. This is equals to hematocrit divided by RBC times 10 to the power 6. Are we here? Per means divided by liter. Are you seeing that? Hematocrit is always in percentage. The final unit for MCV is in femtoliters. You agree with me? There is no percentage in the femtoliter. And you are using hematocrit, and hematocrit is in percentage. This means that you have to divide the hematocrit by 100 to convert it to remove the percentage. So this means that we will get hematocrit divided by what? 100. This division sign will have to be changed. Oh, sorry, here is microliter. Microliter. Are you with me? Here is microliter. So this division sign will now change to what? Multiplication. So that the microliter will go on top. Are we together? Divided by what? RBC times 10 to the power what? 6. When division changes to multiplication, what is at the numerator will come down and the denominator will go up. Are you okay up to this level? Now this is what we will get. We will get hematocrit divided by 100. That is equivalent to 10 to the power 2. Times the unit we are having is femto. We know femto. What is femto? Femto is 10 to the power negative 15. You know that in physics. Femto means 10 to the power negative 15. So this is hematocrit over 10 to the power 2 times. I want femto. In the unit there is a liter. So if there's a liter, I will maintain the liter. But I'd rather be changing anything that is not not in the unit. I have to change it. So microliter. We know micro is 10 to the power minus 6. I have to remove because there's no micro in the unit. Are we there? Times liter divided by RBC count. RBC times 10 to the power what? 6. This is hematocrit divided by 10 to the 10 to the power 2 times 10 to the power minus 6 liter. Please, are you here? Times 10 to the power minus 6. You know where the minus 6 is coming from? This one. When it goes up, it becomes 10 to the power minus 6. Divided by RBC what? Count. Are we here? Okay, so when 10 to the power, by the laws of indices, I'm carrying 10 to the power 6 up here. Then it becomes 10 to the power minus 6. So now I'll get hematocrit over 10 to the power what? 2 times 10 to the power minus what? 12. 10 to the power minus 6 times 10 to the power minus 6 will give you 10 to the power minus what? 12 liter over RBC. I hope you get that. The final unit is femto. Femto is 10 to the power minus 15. What I'm having here is 10 to the power minus what? 12. It is simple. I'll multiply here by 10 to the power minus 3, divide by 10 to the power minus 3. They will still cancel and it still remain the same. Are you getting that? So now I will now get this one to be equals to hematocrit divided by 10 to the power 2 times 10 to the power, I won't cancel it, 10 to the power minus 12 times 10 to the power minus what? 3. That will give me 10 to the power minus what? 15 liter. All divided by RBC times 10 to the power minus what? 3. So, notice what is going to happen. Let me copy this one to the next listen. Hematocrit. So we have hematocrit over 10 to the power 2 times 10 to the power minus 15 liter over what? RBC times 10 to the power what? Minus 3. I hope you can see that. Okay. So now, this will give me hematocrit times 10 to the power minus 15 is now called F femto. Later. Then this 10 to the power 2 and 10 to the power negative 3, when they meet, it will now going to be RBC times 10 to the power minus 1. Are we there? This will give us hematocrit in femtoliters. That is times femtoliters is equals to times this 10 to the power minus 1. I'll send it up, becomes 10 to the power 1. And that is the same thing as 1 divided by RBC. So now MCV will now be equals to the hematocrit value times 10 divided by what? RBC. And the unit will be in femtoliters. So this is the short, the proof of the formula. So anytime you want to calculate the MCV, you take the hematocrit, you multiply by 10, you divide by the RBC, and the answer is in femtoliters. So the next parameter is MCH, which is reported in picograms. So the MCH reported in picograms is the mean cell hemoglobin. And the mean cell hemoglobin is a measure of the amount of hemoglobin contained in the RBC of what? The patient. So you have so many RBCs, and those so many RBCs are giving you a particular HB what? Value. Then if you want to know the amount of hemoglobin contained in a single RBC, then you need to take the HB value of what? The patient, and divide by the number, the RBCs that gave rise to what? The HB. Are you getting that? And that also is a formula, but at the end of the day, it will come with times 10, just like this one. So we know the MCH. So if you want to prove the formula, that is also the same scenario, picogram. This will give me HB. MCH is equals to HB divided by what? RBC. The RBC value is times 10 to the power 6 per microliter. So this means that HB will be divided by RBC times 10 to the power 6 per microliter. Are we here? Then this will give us HB is every number is over 1 times microliter divided by what? RBC times 10 to the power what? 6. So this will give me HB over 1 times micro is not in the unit of what? MCH. It is pico. So I will change it. That is 10 to the power minus what? 6. Is there liter? So I forgot something. It has changed the formula. HB is in gram per deciliter. Actually didn't bring this in. Okay, so let's continue. So times 10 to the power what? Minus 6 liter all over what? RBC times 10 to the power what? 6. But we know that the HB value of the patient is actually in grams per deciliter. The HB value, the unit, whatever value you mention, you always say that maybe 2.5 gram per deciliter. So the value in grams per means divided by what? Deciliter. Are we okay at this point? So times 10 to the power minus 6 liter divided by what? RBC times 10 to the power what? So I don't need to be doing so this will be times 10 to the power minus 6. Are you getting that? I've sent this one up. So this will give me, you see this liter and this liter, they will cancel because the formula does not have liter inside it. So I will now get HB in grams divided by deci. Deci means 10 to the power minus 1 times 10 to the power minus 6 times 10 to the power minus 6 will give you 10 to the power minus what? 12. And that alone is equal to pico. And this liter has already cancelled with this liter. So what I will now have now here is what? Pico divided by what? RBC. This 10 to the power minus 1 could go up. So I will now have the HB value. Pico and grams will be in terms of what? Picograms. But let me send the 10 to the power minus 1 up. That will give me 10 to the power 1. All divided by your RBC value. There is pico here, there is gram here. So the final units become in picogram. So that becomes the formula. So let me give you the last one. MCHC, which is in gram per deciliter. MCHC, this is concentration. And you know concentration is equals what? Amount over what? Volume. The amount in this context, which of the rest indices was defined as in terms of amount? MCH. We said MCH is the amount of hemoglobin in a single red cell. And which was defined in terms of volume was the MC what? Vein. So in other words, MCHC is equals to what? MCH divided by what? MC what? Vein. MCH, this is in gram per deciliter. MCH as the formula is equals to the HB value divided by RBC count divided by hematocrit divided by RBC. Are we together? This will give me HB divided by RBC times RBC divided by hematocrit. This one, cancel this one. We'll get the formula to be HB over what? Over what? Hematocrit. Are you getting that? You see, the MCHC is already in gram per deciliter. Are you getting it? The HB unit is already in gram per deciliter. So we will not want to change anything in the unit of the HB. Gram per deciliter will still be maintained. The hematocrit is in percentage. We need to do away with the percentage. So this means that where we have gotten to in the formula is the same thing as HB, which is in gram per deciliter, divided by hematocrit, But hematocrit is in percentage, so we divide by 100. So this means that you will get the HB value. Let me just remove it. When I finish, I'll bring it back. Multiply by 100 divided by the hematocrit. This implies that the formula will be HB times 100 divided by hematocrit. And that will put the unit in gram per deciliter. Are you getting that? So these are the calculations that are involved in the red cell indices. So once you want to calculate the MCV, you just know that it's hematocrit divided by RBC times 10. MCH is HB divided by RBC times 10. MCAC is HB divided by hematocrit times 100. So these are the calculations involved.